Earth. It may be home to 1 trillion species, but it's just one planet in our solar system that orbits the Sun. And our Sun? It's just one out of the estimated 100 to 400 billion stars in our galaxy, which, in turn, is just one of up to 2 trillion galaxies in the observable universe. But just how big is the universe? In the initial moments following its birth, the universe existed in an unimaginably hot and dense state. As it expanded, it began to cool, creating the perfect conditions for the emergence of matter's fundamental components, quarks and electrons. After a few millionths of a second later, these quarks clustered together, forming the protons and neutrons that would become the heart of atoms. Minutes into the universe's existence, a critical fusion occurred, with protons and neutrons forming the first atomic nuclei. Fast forward the next 380,000 years, the universe continued its extensive cooling period and eventually allowed electrons to settle into orbits around nuclei, resulting in the universe's first complete atoms, hydrogen and helium. 9.26 billion years later, space dust and bits left over from ancient star explosions converged to create the Earth, and everything around us, from mountains and oceans down to a single grain of sand. Now, although it is barely visible to the eye, this grain of sand, which is 0.5 millimeters in diameter, is 5 million times bigger than a hydrogen atom, which is around 1/10 billionth of a meter. However, compared to the size of the Earth, the grain of sand is about 3.92 billionths of the Earth's diameter. But this is just the beginning of trying to understand the sheer magnitude of the universe. For instance, consider the Apollo 11 mission to the Moon. The average distance to the Moon is about 384,400 kilometers. Traveling in a rocket ship with the speed of approximately 7,800 meters per second, it took the astronauts about 3 days to reach the Moon. If you drove a car at a speed of 100 kilometers per hour, or about 62 miles per hour, it would take you about 160 days to cover the same distance. And that's just to the Moon. Traveling in your car at the same speed would take you over 170 years to reach the Sun, which is at a distance of 149.6 million kilometers. This number is already so large that astronomers from the International Astronomical Union have standardized this measurement as the astronomical unit. From here, light takes 8 minutes and 20 seconds to reach Earth. Looking in the opposite direction towards Mars, the average distance from Earth is about 1.5 astronomical units. Although, at its farthest, when Earth and Mars are on opposite sides of the Sun, also known as superior conjunction, the distance can extend to about 2.67 AU. But during opposition, when Mars and the Sun align with Earth in between, this gap narrows to just 0.52 AU. Creating a more optimal window for missions to the Red Planet. However, even at this distance, it would take a spacecraft traveling at 21,000 kilometers per hour, which is the approximate cruising speed of NASA's Mars spacecrafts, approximately 5 months to reach Mars. To put that into perspective, at 21,000 kilometers per hour, you could circle the Earth along the equator in slightly less than 2 hours. Now, zooming out to Pluto, its closest approach to Earth is about 4.28 billion kilometers, or roughly 29 AU. While at its furthest, the distance extends to approximately 7.5 billion kilometers, or about 49.3 AU. Our spacecraft, traveling at 21,000 kilometers per hour, would take about 40 years to travel this distance. If you're wondering how long it would take to drive there in your car traveling 100 kilometers, it would take you 8,500 years to visit this former planet. However, we aren't even 0.05% of the way to the edge of our solar system, or the Oort cloud, where the sun's gravitational influence ends. After passing the sun's heliosphere, which marks the end of the sun's magnetic fields at 123 AU, and surpassing Voyager 1 at 163 AU, we approach the outer edge of the Oort cloud, which lies between 100,000 to even 200,000 AU from the sun. This estimation, however, is based on indirect evidence from comet observations, since we can't directly detect objects at such extreme distances. In this region of our solar system, there are theorized to be hundreds of billions, perhaps even trillions, of icy bodies, and unlike the orbits seen in the main asteroid belt and Kuiper belt, objects in the Oort cloud have a wide range of trajectories and orbital paths around the sun, forming a thick bubble of distant, icy debris, named after the Dutch astronomer Jan Oort. Comets from this region are called long-period comets, as their orbital periods are, well, long, potentially lasting up to hundreds of thousands of years. One notable example is the Siding Spring, known for its close encounter with Mars, an event that won't occur for another 740,000 years. Long-period comets are often observed only once, or have never been seen at all during the existence of our species. Their orbits are so long that some comets haven't been close to the Sun for billions of years since their formation. This distance to the outer boundaries of the Oort cloud from 100,000 AU to 200,000 AU is a remarkable distance that is almost unfathomable to comprehend. 200,000 astronomical units is almost 30 trillion kilometers, or 18.6 trillion miles. To offer some context, consider the longest commercial flight, Singapore to New York. To cover almost 30 trillion kilometers, you would need to take approximately 1,950,074,953 trips. And if you wanted to drive 30 trillion miles, it would take you about 34 million years, or approximately 5,700 times the age of human civilization. However, we are still within our solar system and haven't even crossed 0.003% of the Milky Way galaxy. But before we get there, let's consider the next nearest star system after our Sun, Proxima Centauri. Proxima Centauri is part of the Alpha Centauri star system, which also includes two other stars, Alpha Centauri A and Alpha Centauri B. These two stars are similar to our Sun and form a binary system orbiting each other. Proxima Centauri, also called Alpha Centauri C, is a smaller, cooler red dwarf star that orbits the central binary pair at a much greater distance, making it a sort of distant companion. This star, which is also the most common type in the Milky Way galaxy, hosts at least two confirmed exoplanets, Proxima Centauri B, an Earth-sized exoplanet within the star's habitable zone, where conditions may allow liquid water to exist on a planet's surface, and Proxima Centauri C, a more massive, likely gaseous planet orbiting further from the star. It's also worth noting that there have been some candidate signals suggesting potential planets around the stars in the binary system of Alpha Centauri A and B, although none have been definitively confirmed. Proxima Centauri, the closest of the trio to our solar system, is located about 4.24 light-years away, while Alpha Centauri A and Alpha Centauri B are slightly farther, at about 4.34 light-years from Earth. 1 light year is equivalent to approximately 63,000 astronomical units, meaning a journey to the potentially habitable planet orbiting Proxima Centauri would span about 267,000 AU, or roughly 40 trillion kilometers. And to reach Alpha Centauri A and B would require traveling an additional trillion kilometers. Beyond this system, the next closest star to Earth is Barnard's star, located about 5.96 light-years away. However, if we travel even further to about 40 light-years away in the constellation Aquarius, we find a remarkable planetary system orbiting the ultra-cool dwarf star known as TRAPPIST-1. This system is notable for hosting 7 Earth-sized planets, several of which reside in the star's habitable zone. In February 2018, scientists took a closer look at the 7 TRAPPIST-1 planets and discovered that some of these planets could have a lot more water than Earth. The forms of water, however, might show up as water vapor in the atmosphere for the planets closest to their star, as liquid water on others, and as ice on the ones farthest away. This study also determined the density of each planet very accurately, making the TRAPPIST-1 system one of the best understood groups of planets after our own solar system. Fast forward to 2021, a study published in the Planetary Science Journal revealed more fascinating details about these planets. All 7 of them are pretty similar in terms of what they're made of, showing densities that don't differ by more than 3% from one another. This is quite different from our solar system. These planets are also about 8% less dense than Earth. This small difference is actually a big deal when talking about planets. This might indicate that these planets have a higher proportion of water or other volatile materials, which could have profound implications for their atmospheres, surface conditions, and potential for hosting life. While this is indeed a significant discovery, the distance to reach these planets is equally as fascinating. 40 light-years is about 2.5 million astronomical units, or about 378 trillion kilometers. Taking our previously mentioned rocket ship, which travels at 21,000 kilometers per hour, the journey would take around 2 million years, and by car, it would take 431 million years. Yet, this is only 0.04% of the Milky Way. Considering this scale, the Milky Way is a spiral galaxy with a disk of stars spanning more than 100,000 light-years. Using infrared images from NASA's Spitzer Space Telescope, scientists have discovered that the Milky Way's elegant spiral structure is dominated by 2 major arms spiraling from the ends of a dense central bar of stars. The arms consist of the highest densities of both young and old stars. The minor arms are primarily filled with gas and pockets of star-forming activity. Our Sun lies near one of these arms, called the Orion Arm, or Orion Spur, located between the Sagittarius and Perseus arms, and about 27,000 light-years from the center. The Milky Way might appear small, but in reality, it is so vast that it takes our solar system, which is traveling at around 828,000 kilometers per hour, about 240 million years to complete just one orbit around the galaxy. The diameter of the Milky Way, at 100,000 light-years, is approximately 6.3 billion astronomical units, or about 946.073 quadrillion kilometers. An extremely large number. Yet we are still in one galaxy out of billions or even trillions. The nearest spiral galaxy to ours, which is also set to collide with us in 4 to 5 billion years, is the Andromeda Galaxy. However, this collision between the Milky Way and the Andromeda Galaxy is not expected to destroy our solar system. Although this event will dramatically alter the structure of both galaxies over billions of years, the vast distance between individual stars means that direct collisions are extremely rare. And while 4 to 5 billion years might seem small compared to the numbers we've been talking about, the distance from the Milky Way to the Andromeda Galaxy is about 2.5 million light-years away, or 25 times the diameter of the Milky Way. Furthermore, the Andromeda Galaxy itself is significantly larger than the Milky Way, spanning approximately 260,000 light-years in diameter and hosting trillions of stars. Currently, the Milky Way and the Andromeda Galaxy stand out as the largest and most massive members among the 54 galaxies that comprise what is known as the Local Group, which spans approximately 10 million light-years across and is part of a larger collection of galaxy groups and clusters called the Virgo or Local Supercluster. The most prominent component in the Local Supercluster is the Virgo cluster, which contains from 1,300 to 2,000 galaxies and serves as the supercluster's gravitational center. The Virgo cluster is located about 55 million light-years from Earth and is the nearest major galaxy cluster to us. The cluster itself has a diameter of 15 million light-years, which is not that much bigger than the Local Group, but it contains 50 times the number of galaxies. The Local Supercluster, which contains at least 100 of these clusters, has a diameter of about 100 million light-years, equivalent to around 6.3 trillion astronomical units and almost 950 quintillion kilometers. Remember how far the Oort cloud is from the Earth? You would have to travel that distance 31.5 million times to get this distance. The volume of the Local Supercluster is approximately 7,000 times that of the Local Group, or 100 billion times that of the Milky Way. But if you think that's big, it's just a component of the even larger Laniakea supercluster, which contains over 100,000 galaxies spread across 500 million light-years. This immense supercluster includes the Virgo supercluster, home to the Milky Way, and extends to other major concentrations of galaxies such as the Hydra Centaurus supercluster and the Pavo Indus supercluster. It also comprises individual clusters like Fornax, along with other galaxy groups, all interconnected within the vast network that forms Laniakea. This distance of 500 million light-years is about 31.62 trillion astronomical units, or 4.73 sextillion kilometers, but only 0.56% of the observable universe. For reference, one of the farthest proposed galaxies, HD1, is located about 33 billion light-years away, with a light travel distance of 13.4 billion light-years. This essentially means that the light we currently observe from HD1 left the galaxy 13.4 billion years ago, when the universe was just a few 100 million years old. Since then, due to the ongoing expansion of the universe, the actual distance between us and HD1 has increased, so that it now lies about 33 billion light-years away. This difference between the look-back time and the galaxy's current distance tells us that the expansion of the universe stretches the fabric of space, moving galaxies apart and altering the distances between them. This expansion is measured by HD1's redshift value 13.27, which indicates the degree to which the light from the galaxy has been stretched or shifted to longer, redder wavelengths due to the expansion of the universe as the light travels through space, making it one of the most distant galaxies observed. Moreover, HD1's extreme distance suggests it may host some of the universe's first stars, known as population 3 stars, which were thought to have formed during the reionization period following the universe's dark ages. However, this distance to HD1 is only 35.5% of the diameter of the observable universe, which is thought to be around 93 billion light-years. This is about 5.88 quadrillion astronomical units, or about 879 sextillion kilometers. To begin to even understand the magnitude of this, let's start with our Milky Way, which is 100,000 light-years in diameter, meaning that the observable universe is almost 930,000 times bigger. So let's say a grain of sand represents the Milky Way. This is 10 grains of sand. This is 100, 1,000, 10,000, and 930,000. The fastest human-made object ever built, the Parker Solar Probe, which travels at around 635,000 kilometers per hour, will take about 170 million years to travel the length of the Milky Way. And to travel the length of the observable universe, it will take about 158.5 billion millennia, which is about 11,500 times the age of the universe. And if you want to drive there in your car, it will take about 1 quintillion years, or about 1 quadrillion millennia, which is almost 73 million times the current age of the universe. And just for fun, here's how many years it would take to walk there at the average walking speed of 4.8 kilometers per hour. But this is just the distance of the observable universe, which refers to the portion of the entire universe that we can potentially observe from Earth. Given the finite speed of light in the age of the universe, since light travels at a constant speed, we can only see light from objects that have had enough time to reach us since the beginning of the universe. This creates a horizon beyond which we cannot observe, because the light from there hasn't had enough time to reach us. For example, the Milky Way is about 100,000 light-years in diameter, meaning that light from distant stars within our galaxy can take up to 100,000 years to travel across and reach us. When we observe these stars, we're seeing them as they were tens or even hundreds of thousands of years ago, not as they are at this moment. However, the universe's expansion rate surpasses the speed of light due to the stretching of space-time. This means that distant galaxies are receding from us at velocities that can exceed the speed of light, making the universe's actual size increase more rapidly than our observable horizon expands. So at some point, all the stars we see when we look up at night will be gone, and we will only see darkness, illuminated by the light of stars only within our galaxy. But that will happen over tens of billions of years, so you can enjoy the starry night sky and admire the vastness of the universe.